In this class, we study more about Dirac equation. Actually, in the previous class, we have derived the Dirac equation, right? And Dirac equation is written like that. Hamiltonian is linear in momentum multiplied by some matrix, and linear in mass and multiplied by some matrix. And we have shown that only from 2 by 2 matrix, 4 by 4 matrix, such kind of matrix exists. The reason is that the square of this Hamiltonian must reproduce the energy momentum relation. And if I square this, I have alpha dot p plus beta m squared. And the p square factor has alpha I, alpha j. And crossing term is a pi alpha I beta, beta alpha I m. And beta squared term is a beta squared m squared. And that must be the same as a p squared plus m squared. That gives alpha I alpha j plus alpha I must be 2 times the Kronecker delta. And linear term in momentum must vanish, so that alpha I and beta must anti-commute, and beta squared must give identity. So that constraint gives the minimal matrix such that alpha equals a sigma matrix in the off-diagonal term, and beta is 1 minus 1, 4 by 4 matrix. It is easy to find that from this matrix directly. You can show that alpha I and beta, both of them are Hermitian. But before doing that, using this factor only, you must be able to find that alpha and beta are Hermitian. And sigma matrices are given in this way. Sigma 1 is 1, 1 in the off-diagonal term. Sigma 2 is minus I, and sigma 3 is diagonal 1 minus 1. Why don't we find covariant form of the Dirac equation? Covariant form we must make use of the covariant derivative. You know, we have time derivative and spatial derivative in momentum. So there must be some way to find the covariant form. Okay, why don't we move everything to the left-hand side? Then Hamiltonian, and momentum is now in the flipped plus I, alpha dot gradient, and this term becomes minus beta m. Here, I'd like to multiply beta matrix because I have a simple constraint that beta squared is 1. If I multiply beta both sides, the right hand side is 0, and this term becomes just minus m because the beta squared is 1. So I have matrix here and another matrix here with additional factor beta. Now, why don't we define these matrices beta and beta alpha? There are 3 matrices, and just treat this one as a 4 vector because there are four matrices. Sure, it has its own Dirac structure that has a 4 by 4 matrices. However, it has a vector index, 0th component and the spatial component. Then it is multiplied with covariant derivative. If I multiply them, I have plus sign. So I can reproduce the scalar product style. So if we define gamma matrices like that, whose 0th component is beta and the spatial component is beta alpha, then this is just gamma, mu, round mu, something like that. Okay? So, this is just gamma mu, round mu. Right? And minus mass. This is the covariant form for the Dirac equation. Here, gamma matrix is defined to be gamma 0 is beta. Beta is here. And gamma vector, which is also matrix, is beta alpha. If I multiply beta here, beta and alpha, alpha is here. Then I have 0 minus sigma, sigma 0. Okay? So, spatial component of the gamma matrices are sigma minus sigma, which still have the off-diagonal term. Then our next question is that what is the Lagrangian that produces this equation of motion? To make it short, just let me give you the answer. This is the Lagrangian, where this psi bar is defined to be psi dagger multiplied by gamma 0. Okay? So, this is psi dagger and gamma 0, and I copied the remaining part. If we derive the equation, minimize the action by making use of psi dagger, it is simpler, but for educational purpose, let me derive the equation of motion by making use of the variation of psi. As we learned in the previous case for the scalar particle, complex conjugate field is independent of original state if it is charged particle, right? So in general, psi and psi dagger are different independent fields. So minimization of the action can be made in a separate way. So if I find the Euler-Lagrange equation that is like that, any field's derivative, derivative, and take another spatial derivative for each indices and subtract the Lagrangian's derivative with respect to that field. If we compute this, derivative is given in here, so what I do is just pull out over a factor of this guy, right? That is this. So psi dagger, gamma 0, gamma mu, and I have factor of I. If I take the derivative with respect to psi, then I read mass with gamma 0 factor. And minus sign cancels this negative sign. If I combine both of them after taking the derivative, then round mu, I, psi dagger gamma 0, gamma mu. And right thing is a plus m, psi dagger gamma 0 equals 0. It is rather complicated, but if I want to find the equation of motion for psi, it's better to take the complex conjugate. For the matrix, we take the Hermitian conjugate. And if I take the Hermitian conjugate, simple cases, gamma 0 dagger and psi, right? That is this, right? But gamma 0 is what? Beta, and beta is emission. So this is just gamma 0 psi. Gamma 0 psi. Then next, consider this. remember that this derivative acts only on psi. Psi has x dependence, but these are just constant matrices. If I take the derivative to those matrices, it just disappears. So this is constant. So if I take the complex conjugate, order is flipped. So gamma mu is here with dagger, and gamma 0, dagger is gamma 0, gamma 0 is beta, and then psi dagger becomes psi, and complex conjugate. Hermitian conjugate, once a Hermitian conjugate acts on a complex number, it becomes a complex conjugate. So I have minus I. I have rather complicated object, gamma mu dagger. It can be computed component by component. For the zeroth component, gamma 0 dagger. Oh, it's a beta. Beta dagger is beta. So beta is gamma 0. It is the same. What happens to the ith component? Ith component is beta alpha I, and Hermitian conjugate is flip the order and take the complex conjugate for each case. So alpha I dagger and beta dagger. And as we know, alpha I and beta, both of them are Hermitian matrices. So just alpha I beta. But I have anti-commutation relation. Alpha I beta is a minus beta alpha I, right? So I have negative sign. Beta alpha I is gamma I. So gamma mu dagger is like that, where gamma mu equals gamma 0 gamma. So just like it is just like gamma mu. So contravariant becomes covariant. Okay? So it is wrong. Why? This derivative must act on, this derivative is covariant, and this derivative must be coupled to contravariant one. We have to correct this relation. One of the ways is just multiply gamma 0. We have this kind of relation. This is homework. It is very easy to show using everything shown here. If I multiply gamma 0 to gamma mu dagger, it becomes gamma mu lower index, but when gamma 0 commute, gamma 0 and gamma I we combine everything together. Our anti-commutation relation is 2 times G mu nu I identity. So if you show that, it is easy to show that gamma 0, triple gamma 0 is a beta q, and any beta squared is 1, so it is beta. So it is the same. But the spatial component, if it is I, it changes its own sign. So here its sign is flipped due to the dagger for the spatial component. But again, gamma 0, when it anti-commutes, it flips the sign for the spatial component only. So the sign flips to twice, it becomes the same. So it is just gamma mu, upper index. So if I make use of this fact, then I just multiply gamma 0 to the left hand side. Then what is that? This is just gamma mu up. And gamma 0 squared is just identity. So what I have is, it becomes identity, and this guy, because of this relation, is replaced with gamma mu. And as we know, gamma mu is constant matrix. So if I take the derivative, it just this derivative just pass and it acts on the side. And we just multiply -1 to both sides, then it becomes Dirac equation of the covariant form. Okay, that's it.